In this part of the lesson, we're attempting to derive the formula for Newton's method, and that formula is xn plus 1 is equal to xn minus f of xn, where f of xn is divided by f prime xn. Now, you did look at this derivation on the last website, but that may not have made a lot of sense to you, so we're going to take a look at it again. What you can see at the top of the screen here is a function f of x drawn, and it has a 0 or root at r. What we're going to do is make an initial approximation, x1. And what I've done is drawn a tangent line to the curve at x1. So that means that that tangent line shares the point x1 and f of x1 with the curve itself. Well, if we follow down along that tangent line, you will notice that it has a 0 or root, and it is at x2. x2 is closer to r, the true 0 or root of the function, than x1. So x2 is a better approximation than x1. So how would we go about finding x2 knowing x1? Well, that's what the formula in your study guide and the formulas or equations or derivations you see on this screen are trying to illustrate. First of all, we have y minus y1 equals m times, in brackets, x minus x1. You may not be aware, but that is the general equation of a straight line or linear function. You're used to seeing it in the form y equals mx plus b, but this is a alternate form which is perfectly acceptable. In order to define the function in this form, what I need is the slope, m, and I need one point, which would be my x1 and y1. Well, if you think about it, our tangent line is a linear function, and what we would like to do is see if we can find x2 on our linear function, or the 0 of that linear function. Well, we take that general equation of a linear function, y minus y1 equals m times x minus x1, and we start filling in for what we know. Well, our y1 I'm no longer going to call y1, I'm going to call it f of x1. That is indeed a point. That is the y-coordinate of a point on my tangent line or linear function. It's going to be equal to my slope, which in this case is going to be f prime x1, because my slope of this linear function is actually the slope of the tangent line. That's why I've written f prime x1. I multiply that slope by x minus x1. Okay, now we have to say to ourselves, well, what we want to find for this linear function is its 0 or root. Well, the 0 is the same thing as the x-intercept, and it occurs when y is equal to 0. So we substitute 0 in for y. So we now have 0 minus f of x1 equals f prime x1. And what we're going to do is call our other point that our x-coordinate for that 0 is going to be x2. So we have x2 minus x1. So to recap, what we have is a point, x1 and f of x1. We have the slope of the tangent line, which is f prime x1, which has been filled in. We know the y-coordinate of our 0. It is 0. And we'd like to find the x-coordinate of our 0, which is x2. So we want to take that equation and rearrange and solve for x2. First thing we do is divide both sides of the equation by f prime x1. So we end up with negative f of x1 divided by f prime x1, and that's equal to x2 minus x1. Remembering that we are trying to solve for x2, the 0 of our tangent line. we rearrange such that we get x2 is equal to x1 minus f of x1 divided by f prime x1. So this expression allows us to solve for x2 if we know x1 and we know the equation of the. We've drawn another tangent line to our curve. That tangent line was found by taking x2, a better approximation for r than x1, and going up to our original curve f of x, and we're going to draw a tangent line to the curve at that value of x, x2. Well, the zero of this new tangent line is x3. Hopefully you can see that x3 is even a better approximation for the zero or root of this function than our x2. How would we have gone about finding that particular value for x3? Well, if you had repeated the same procedure that we had used previously, you would have found that x3 is equal to x2 minus f of x2 divided by f prime of x2. So at this point, we've learned that x1 was our initial approximation for the root of this particular function, that x2 was a better approximation, and it could be determined using the formula x2 is equal to x1 minus f of x1 divided by f prime of x. And then we drew another tangent line to the curve at x2, and we found that its zero, x3, was even a better approximation. And x3 was found using the formula x3 equals x2 minus f of x2 divided by f prime x2. From this, one can conclude that all successive approximations could then be determined by using the formula x subscript n plus 1 is equal to xn minus f of xn divided by f prime xn. This is the general formula that we use when attempting to find the zeros of a function using Newton's method.